Hi everybody, I'm going to go over epoxidation in this video. So we've seen epoxidation reactions previously. We originally did them by, oftentimes we'd be starting with alkenes, mostly because I was trying to get you to use alkene reactions, but we'd often start off with a hydrohalogenation using something like bromine and water. That would give us the halohydrin. Okay, and then we'd finish that off with something like a strong base to deprotonate that alcohol, which can then act as a nucleophile and do an intramolecular SN2 reaction. So that we'd end up getting something like this. Well, I guess we'll do it on the side that the oxygen's on. Okay, so we'd end up getting that plus the enantiomer in this case, because this would be racemic. Okay, so that's how we did it previously. You could do that with cis and trans alkenes. So the cis alkene version would look like this. We've got that nice anti-addition, which sets us up very nicely for the attack with the SN2 reaction. In this case, we didn't form an enantiomer because it's not a chiral molecule. It's got a plane of symmetry there. It's actually meso. Okay, so that's how we had been doing epoxidation previously. Not really the most efficient way of doing epoxidation, but it definitely works. But there's another way that is nice and one step. So it's kind of the industry standard essentially for actually making epoxides. Most people would do it this way rather than the way that we learned previously. And that is using MCPBA. Okay, and we will talk about what MCPBA is, but at the end of the day, it makes exactly the same products, but it does it in one step. Okay, so MCPBA equals meta chloro peroxy benzoic acid. Okay, the important part of MCPBA is this peroxy bit. Okay, you can pretty much use any peroxy chemical to do an epoxidation reaction. MCPBA is just the one that people use all the time, and it's nicely commercially available. It's pretty stable. So MCPBA is usually the one that people will grab, but you can use any peroxy acid and it will do an epoxidation reaction in most cases. So if you draw it out, this is what it looks like. So you've got a benzene ring, you've got a meta chlorine, which is meta to the peroxy benzoic acid part. And that is what a peroxy acid looks like. So a carboxylic acid, remember, is just the one OH. This one just has that extra oxygen in it, which is what makes it the peroxy. It's like an extra oxygen. Okay, so having this oxygen-oxygen bond in there, think about like hydrogen peroxide. The perox is oxygen-oxygen. Okay, but that oxygen-oxygen bond is quite weak. And so we will see that in this mechanism that will end up breaking that bond because it's a pretty weak spot in the molecule. Okay, so the mechanism is actually kind of a fun one, I think. So I'm going to show this mechanism just on the cis alkene. Okay, oops, but it's the same on the trans. But I just want to be very clear about what's happening to the shape of the alkene and how it's not going to be changing at all. So if we've got our peroxy benzoic acid, And I'm going to draw this in kind of an odd way, but you will understand why I'm drawing it that way in a second. Okay, so I kind of have this piece pointed rather suggestively at the alkene. So this is actually the oxygen that's going to be making our epoxide. So that's where the oxygen is coming from. So we're essentially making those bonds, okay? But there's obviously stuff that has to happen in order to free up that oxygen to make the epoxide itself. So I'm gonna do this slow. Okay, so we know that the oxygen-oxygen bond is weak. Just like when we had, think about when we have brominations, for instance, of alkenes. We talked about the bromines not necessarily sharing evenly the electrons between each other, and you might have one that's delta positive and one that's delta negative. We're going to see the same kind of thing here. So we're actually going to have the alkene go and attack that oxygen, which then breaks that oxygen-oxygen bond. So it can form a new oxygen-carbon pi bond. And then we obviously have to have these electrons go somewhere. So those are going to go grab that H. And then those electrons can make the other side of the epoxide and make that other CO bond. Okay, so this is just acting as a proton. So we're going to get protonation here. This bond is breaking, this bond is breaking, and then these two bonds are forming. Okay, so if we were going to number this out, this would be step 1, step 2, 3, and 4. And the numbers here don't really mean a whole lot because this is a concerted mechanism, so they're all kind of happening at the same time. But it kind of helps me to think about a certain chain of events occurring, just kind of in my head. But just keep in mind that if there were actually steps here with intermediates, I would have drawn those out, but there are not. So this is all just kind of one step. And then we end up getting out our nice new epoxide. And then if we think about what we've made over here, we've got a new double bond there. We used the pi electrons here to protonate there. So essentially what we made is we made a new carboxylic acid. Okay, so if we were to draw that out, I'm going to make sure I don't do any bond rotations at all so that we can be very clear about what happened here. So it's going to look kind of funky in the way I draw it, but okay, so we essentially made that. So that is the mechanism of the epoxidation. Kind of a fun one. You can see it all moving around. But the important thing to keep in mind is make sure that we're staying with the same alkene geometry here. So if I have a cis alkene, I'm making, you know, that chain is still in the same position because there is no opportunity for rotation here. So our alkene is going to decide what kind of geometry our epoxide has. So just keep in mind that if you've got a trans, you're going to see them turn out like that. If you've got a cis, you'll see it turn out like that. So make sure you don't do any bond rotations while you're making the epoxide, and then it'll all be fine. So we're just going to write that as a note. So this is stereospecific based on alkene. Okay. All right. So the alkene determines epoxide stereochemistry. Okay. So that's pretty much it for epoxidation. This is just to kind of give you something that's a lot easier to use, quicker to use. You don't have any issues of, you know, maybe you've got something else that can't handle bromine and water. You don't want to throw a base in, whatever. This is an option to use instead. and it's really handy, it's really fast. And this is kind of how people do it. So let me know if you have any questions. And if not, I will see you all later.